Theorem, the symbol for momentum. Lowercase p. The equation for momentum is what? Flat.
Delta pi equals delta pi. Oh, my bad.
We'll try again. Vlad, what is the equation for momentum? It is, in fact, on the handout I gave you.
mv.
Mass times velocity. What is missing from this equation, Sarah Jane Jones?
Vectors.
Vector symbols. For those of you who took the multiple choice question quiz, it was the vector symbol that tripped many of you up. Please remember that momentum is a vector. Newton's second law from this chapter, the more general version of Newton's second law. John?
Sum of the forces equals the derivative of momentum with respect to time with vectors on momentum and equals.
What then is the difference between this and the net force equals mass times acceleration? Emily?
That accounts for the changing mass.
This accounts for the fact that mass can change. Good. Let's see. When do we know momentum is conserved? Nitish?
When the net force is 0.
When the net force is 0. When all the forces adding on it add up to 0. In other words, all the forces are internal. Then the derivative of momentum as a function of time means the momentum is not changing. You get the net momentum initial is equal to the net momentum final. Vlad, I think that's what you're referring to instead of deltas, though we have nets. Please don't forget that you need to be able to work with this with unit vectors I, j, and k. Those are important. Also remember that we can rearrange this equation, net force equals the derivative of momentum as a function of time, all the way to get to the fact that we have, let's do it this way, the integral of the dp is equal to the integral of the net force with respect to time. In other words, the change in momentum equals the integral of the force with respect to time. A couple things. First off, what happens to the net force? What happened to the symbol for the net force when I went from one equation to the next? Please. It disappeared. Why? Mohit.
Oh, I'm just going to say disappeared.
Ah, disappeared. Well, I'm sorry. The why is what I mean. It's an assumption we make during all collisions. Spencer?
Because all the other forces are very small comparatively.
It's called the impulse force approximation. During a collision, we generally assume that the force of impact is the largest force and all the rest of the forces are small enough where we can ignore them and they are negligible. Therefore, the net force would be the force of the collision. This is equal to what symbol? The change in momentum. Meg?
Not quite sure.
Symbols. Who's got one for me? Zach?
J.
It's also equal to, Sarah Jane? I. Both J and I stand, Hillary, for?
Impulse.
Impulse. The impulse, sometimes we see J, sometimes we see I. Remember, this is from time initial to time final. And note that this is not the equation for work. What is the equation for work? Bailey?
It's force.
I'm sorry, the one where the force is changing, not a constant force.
Then the integral of force with respect to position.
Note how similar they are. They are different equations, however. Remind me, what is the integral if the derivative is the slope of the line? Yuchen? What is the integral if derivative is the slope of the line?
The integral would be the area under the curve.
Under Michael meaning?
Below the x-axis, and it's like negative above the x-axis.
I agree with this. Yes, there's more to it. That's part of it. What's the other part? So between the curve and the x-axis, where below is negative and above the x-axis is positive. Recall as well that we, in addition to this equation, we also had that the change in momentum was equal to the force average multiplied by the change in time. So rather than dealing with a changing force, you could just deal with an average force, and that is sometimes something you will see. We had two different types of collisions. Please give me the two different types of collisions. Kathy?
Elastic and inelastic.
Close.
Perfectly.
Perfectly. Now I'm going to put perfectly in parentheses. And we had to talk about whether momentum is conserved and whether kinetic energy is conserved during these various types of collisions. Is momentum conserved during, actually, I'm sorry, let's start with the one-word definition of elastic and perfectly inelastic collisions. Stacey?
Elastic, the word is bounce. Perfectly inelastic is stick.
During an elastic collision, the two objects bounce off of one another. During a perfectly inelastic collision, the two objects run into one another and stick to one another. During an elastic collision, Gary, is momentum conserved?
Yes.
How do you know?
Because it returns to the same spot as
Sorry, that doesn't make sense to me. It returns to the same spot it starts from. That doesn't make sense. That doesn't have to do with conservation of momentum. That would have to do with conservation of kinetic energy, I think. Help us out. How do we know momentum is conserved during an elastic collision, please? Bill?
Because it's internal.
Because all the forces are internal during the collision, right? So during all collisions, we're going to have momentum is going to be conserved because all the forces will be internal. Is kinetic energy conserved during a perfectly inelastic collision? Sierra?
Yes. No, wait, sorry. Perfectly inelastic.
That's what I said.
Sorry.
I know. I didn't go in order. Why would I do that? Sierra, we'll try that again. Is kinetic energy conserved during a perfectly inelastic collision?
No.
No. What about during an elastic collision?
Yes.
Please explain why the parentheses is there in front of perfectly inelastic. Why do I have this? It's an important piece. Len?
Well, because it's physically impossible.
Actually, it's not physically impossible to have a perfectly inelastic collision. It is physically impossible to have one type of collision, but that's not the one Jenkins said.
Are almost all collisions inelastic?
Almost all collisions are inelastic. The two extremes, the ideal cases are perfectly inelastic and elastic. It's very difficult to have an elastic collision where the two objects bounce off of one another and kinetic energy is conserved. That's something you can have on an atomic level. The two objects actually have to not touch when they collide with one another. So that's something you have on an atomic level. So most collisions are inelastic, where the two objects bounce off of one another and kinetic energy is not conserved. But we generally talk about the two limits, which are an elastic collision and a perfectly inelastic collision. We have the equation for the center of mass. What is the equation for the center of mass, Travis? This is for a system of particles.
Is it 1 over mass total or just mass?
Help him out. Who's got the one for a system of particles?
Is it mass 1 x1 plus mass 2 x2 all divided by mass 1 plus mass 2?
I'm going to put dots here just to indicate that we could have an infinite number if we wanted to of different pieces here or particles. And what is x in this? x1, x2, for example, Tim?
Location.
What is x? Go ahead.
Distance from the axis of rotation.
It's actually not the distance from an axis of rotation. That would be if we were talking about like the moment of inertia, for example. This is not. This is the center of mass to silicon.
It's like a distance from an origin on the other side.
It's simply from a reference line. You get to pick where that reference line is. That's all it means. It's just the distance from a reference line. That's for particles. What about the center of mass for an object with shape? The equation for the center of mass for an object with shape, please, Mr. Patel.
Would that be 1 over total mass of the integral of the r
With respect to what? Taking an integral, it's got to be with respect to something.
Yeah. That'd be d something.
Yes, d something. Thank you for clarifying. Jenkins.
dm.
With respect to the mass. Thank you, Mr. Patel, for making this mistake. It is an important one because it's one that happens all the time. Zach. R is not squared. What is he confusing this with? And it happens all the time. Meg, the moment of inertia. So it's important to make that clear, the difference between the two. This brought up, yes.
One question. If you're finding the center of mass, like say you have the x center of mass, you have to solve for the y center of mass?
You could solve for the y center of mass. You could also solve for the z center of mass, et cetera, et cetera.
So it doesn't really matter?
Well, I mean, if you're trying to figure out exactly where the center of mass is, yes, you would have to do it in various directions as well.
Okay.
But usually we'll just do it in one direction. It's redundant.
So like on a test, if you say solve for the center of mass, just one?
I usually identify which center of mass we're talking about.
Okay.
Because it's highly redundant to do it in more than one direction. Yes.
Which R and X?
R, is, yes. I mean, sorry, actually you could put R's here instead. You could put Y's. It doesn't really matter. R, just X, just give a direction. Yes, Meg.
So the equation we have is for object without shape.
Particles. This one's an object with shape. Particles generally were just considered to be objects where the shape is irrelevant relative to the size of the particle. Okay, this brought up 3 different types of densities. Tyler, give me all.
All right, we've got volumetric density,
Symbol?
rho, and that's mass per unit volume.
Good. Volumetric mass density?
You have linear density, which is a lambda, I believe.
Yep.
And that's mass per length.
And the one we have yet to use?
And then it's like sigma, I think.
It's a
For that
lowercase
one.
sigma, yes.
That is, what's that one? Surface mass density, which is mass per area.
Thank you for reading that too. Okay.
If you got it.
So we have, that is everything in Chapter 9. Chapter 10 was circular motion. We have 3 equations from Chapter 10, only one of which is on your equation sheet, and that is that the tangential velocity equals r times the angular velocity. What equation will go above this one? Henry.
Let's see. Displacement is equal to
Bless you, Matt.
right?
What type of this? Right. It's not x though. Okay. Hunter.
Is that S equals what theta?
S equals r theta, because what you're talking about is the displacement, linear displacement when you're moving in an arc, which is called the arc length. What goes below this equation, Spencer?
Tangential acceleration equals r efficient.
R times alpha angular acceleration. Why do these 3 go in this order, John?
Because you can derive arc length to get the angular velocity.
So you can take the derivative. Derive is a more general term. You can take the derivative with respect to time of the first to get the second, and the derivative with respect to time to get the third. So, great. We have Angular velocity equals the derivative of angular position as a function of time. We have the angular acceleration equals the derivative of the angular velocity as a function of time. All of these. We have U fishy M. What is the full title of U fishy M, Vlad?
Uniformly angularly accelerated motion.
Very nice. We have two different equations for the centripetal acceleration. Travis, two equations for centripetal acceleration, please.
Mass, velocity tangential squared over r, and r omega. It's not squared.
Well, is it or is it not?
It's not. It is.
Is it tangential velocity?
Yeah. What? Oh no, okay, yeah. Not squared. Oh, r squared. There we go. Omega.
R omega squared. All right, there we go. Okay. We have rotational kinetic energy. What is the equation for rotational kinetic energy? Please look.
Oh, kinetic energy.
Good. Moment of inertia. We have two different equations for moment of inertia. Please give me both. Doorstep.
So it would be integral of r squared with dm.
With respect to mass. Nope. Similarity. Not the same.
And then it's also the sum thing.
Sigma.
Mass r squared.
I'll put the i's on here just to identify that we could have I, from 1 to however many we have. What is the difference between these two equations? Henry. They're both for a moment of inertia. Help Henry out, please. Sarah Jane.
The second one's for particles.
First one,
Objects with shape.
objects with shape. Bless you. What is R in both of these equations, Jenkins?
It's the distance from the axis of rotation.
Good. R is the distance from the axis of rotation. Moment of inertia is what this is. What is another term that I like to use for moment of inertia, Michael? Helps you to understand what it actually represents.
The rotational.
Great, rotational mass. You need to be able to derive the moments of inertia for about the center of mass for the ones that we did in class. We did which one did we do? We did the thin rod. We did the thin hoop. We did the solid cylinder. Yeah. Those are all ones that you are responsible for being able to do. The parallel axis theorem. What is the parallel axis theorem? I'll take it from whomever has it. Doorstep.
It's not when I try to find the moment of inertia not at the axis of rotation.
Not at the center of mass.
Oh, yeah.
Yes?
And when we
Yep.
Okay, so it's the moment of inertia center of mass plus mass times d squared.
What is D in this equation? Look. Okay. What is D in this equation? Miller.
The distance from the center of mass to the new axis of rotation.
It's the distance from the center of mass to the new axis of rotation. Note, again, this is not on your equation sheet. What must be true of the object in order to use the parallel axis theorem? Jenkins.
It has to be uniform.
Has to have a constant density, it needs to be uniform. we have equation for torque. Torque equals RF sine theta. We also have net torque equals I times alpha. Remember, you have to identify your axis of rotation whenever you're summing the torques. Rolling without slipping. Just remember that you have both translational and rotational motion. Therefore, you have both kinetic energy translational and kinetic energy rotation. Usually you end up using conservation of energy as well. We did that. And on the left.